40,000 a kilogram. In the future, maybe 10 years, when certain, optimistic rocket companies manage to reduce the cost a whole lot, maybe that cost of GEO will get down to around $4,000 per kilogram. So we could view that in 10 years, that's the value of this stuff. But that's still a lot. And the important thing is, even if an asteroid contains 50 parts per million of platinum group metals, and 10% nickel iron grains, 10% water, well, those are worth like $1 million in orbit each. And the platinum group metals would be worth about $4,000 per ton of ore. So, let's see, but we do think that all the mass will have value. And the value proposition is very good, we think, once the market is developed. There is no market for this stuff in high Earth orbit today. That is our challenge. There are markets on Earth, but it's expensive to get things down to Earth. Now, the important thing is we do believe that near-Earth asteroids will be a major resource opportunities for this century. That's where things will be coming from. That's where all the excitement will be. I'll talk a little bit now about the Microgravity Foundry. Basic concept is we take asteroid bits in and produce finished metal products out. So it's a very simple process. Very simple concept. Process isn't quite so simple. And it's basically a 3D printer that prints high quality metal parts, such as nickel or iron. Current 3D printer technologies either use extruded plastics, sintered or cemented aggregates. They take metal powders sometimes and heat them up and melt them together. They extrude metal wires, or they extrude plastics, and solder them together in various ways. But what we're doing is a bit different. It uses a gaseous media for the carrier for the metal. Instead of a powder or anything else, it deposits the metal out of the gas at a low temperature, relatively speaking. It's not anywhere near the melting point of the gas. Doesn't require a gravity field, works in space, and we believe it produces really high quality. Well, initially we're going to focus on nickel because we know we can produce high quality nickel parts. We believe we can produce high quality parts of other metals, including things like iron, cobalt, titanium, and even platinum, if you want to build parts out of platinum.
Is this been done on Earth? I'm not familiar with any 3D printing that has gas as an input. Is this been done on Earth?
No, it has not, and we have a patent pending for this process, and we expect it will have great value on Earth. We're focusing on space. We expect to license the technology to mainstream 3D printing companies to develop those things on Earth, although there are some other companies that are potentially interested as well that aren't current 3D printing companies, but are rather nickel and iron production companies. Let's see, interesting thing is it does use any source of metallic nickel, which could simply be just nickel powder we provide, or asteroid nickel iron grains, or what I think is very interesting, nickel parts. That means if you have a spacecraft traveling to Mars, for example, and it has a widget that breaks, that's made out of nickel, we can take it, pop it into our machine, we grind it up, and turn it into a gas, and rebuild the part. As good as new, right there, didn't even require any extra parts. So we are really excited about this. We think that's a real green technology because it can recycle all of its own outputs. Doesn't have any consumables except for the nickel that goes into the part, and there's no waste. We don't produce any waste products in this process, except heat. Always can't get away from integrators. Let's see, we do plan a phased development. Our first phase is a technology demonstration. We have started working on that now, we hope to have that completed within about 6 months. The second phase is a fully functional 3D printer, which will be intended for Earth markets, and we will be testing it on Earth, making film. We then have a slightly larger, fully functional 3D printer in space that adds the extra stuff to also recycle nickel metal parts and asteroid bits and stuff, and that's something we want to test in the third phase. And then in the fourth phase, we have a plan for a full-scale in-space manufacturing facility which can custom print large devices like, presses and things like that, which are used to mass produce other things in space. So you wouldn't use, we don't think we use a 3D printer for mass production. It just takes too long. What you do is you build the machine, the tool that does mass production, and then you can spit out, lots of sheet metal or extrusions or I-beams or whatever.
You do.
So let's see.
Where are you going?
What about the
Oh, okay.
development on Earth of these things? Are you working with companies to help develop these technologies, or universities, or pursuing grants and such to do that?
For this, we aren't really working with anyone at the moment, except with NASA. And we've talked to a bunch of universities, including Purdue, which they have a bunch of research parks in Indiana. So, and we've talked to some Purdue people about that. Where we end up doing this is one of the questions that I've been pursuing. So we want to put this somewhere, preferably in a place where we can do research. A research park would be ideal. So, but we haven't, yes.
Oh, yeah. Are you done?
Oh, yeah.
Okay. Yeah, the question is, when it comes to printing out large tools, the difference between, say, gravity and near gravity situation like gravity. Would that make a difference in the functionality?
We're sure it does.
Yeah.
On Earth, we tend to use gravity and large, heavy things to apply pressures when you're stamping or things like that. Rolling mills, they tend to use larger. But the reality is you don't need gravity to do those things. All you need is to squeeze it. So you need strong parts that can squeeze together, and then you can extrude, you can produce sheet metal, roll out long sheets. That's really mostly squeezing, and you don't need gravity to do squeezing. Doesn't mean there's not some issues. There's a lot of things we haven't worked out the details for. Nor do we expect to do that on our own. We expect a lot of these things will be done with consortiums. One of our proposals, okay, this is internal, I haven't told you. One of our proposals is for, once we bring back a large chunk of asteroid ore, we want to have an ability to send up lots of processing things. If you can imagine, if every university could put together a 1 cubic meter, device to be launched, and we would attach it to our asteroid and feed it the feedstock at once, and then they could do something with it and try to process it. That's one of the things we're talking about doing. Getting 50, even 100 different universities and companies and stuff all to cooperate in how to do this, because there's a huge amount of stuff that has to be done, and there's an incredible amount of stuff that we have to learn. We'd like to do that jointly. We'd like to be able to take advantage of those things, and we want to put together an environment which fosters educational university cooperation, and everyone wins, we think. So it's one of the things we'd like to do. Of course, the Microgravity Foundry is useful in a lot of places. Any place that's way far away from supply sources would find it valuable to have a 3D printer that can build these high-quality metal parts. Some are kind of obvious in space, and we think that every deep space mission will probably want something like this if they've got any room at all, because it certainly makes it easier to survive if everything can be repaired instead of having to work perfectly the entire mission. It's a different kind of engineering if you do that. I gave a talk at the Tennessee Valley Interstellar Workshop where I was proposing that these microgravity foundries would help us do something else that's useful in a long future, far distant future, 100 years from now, interstellar mission, and that's that you want the people who are traveling to another star system to start a new human colony, you want them to be skilled when they get there. You don't want the first time someone looks at a manual for something to be, 2 generations before the guy that has to repair the part. It's not a process for success. If you engineer everything to have a 100-year lifetime and something fails 80 years into the mission, when you still need it, because they won't know how to fix it. Instead, engineer things so that they break, and you have to repair them all the time. It'll keep your skills up, and well, something like that could be an important issue.
So then are you looking at this to be human in the loop process, or is it more automated?
Well, this microgravity foundry is basically an automated process. Humans decide what part they want and start the process, and it makes it, and then they take it out and assemble it into whatever it has to be assembled into.
So it is a human in the loop. You're expecting
There's human in the loop,
humans
but not to make the widget.
Gotcha.
So if you want to make the widget, that's separate. But incorporating and repairing something, we're not doing robots and stuff to do that. There are, in our 4th generation, we do have robotic arms involved because we can do some interesting things like our process. I mentioned it was low temperature. That means we can take another little gadget that's not made out of metal, let's say a Teflon bearing. We can hold it in place and build the metal around it, and it will work. And so we can build the structure around parts that aren't nickel metal. And we think that's an exciting possibility. And so we will have robotic arms for that, but that's not going to, we're not going to use a robot to take the part out and put it into something else. There are terrestrial applications for this as well. We think aircraft carriers and submarines are a good site. Rapid prototyping is what most of these things are used for now anyway. Most 3D printing is used for rapid prototyping. Also, you can build things that can't be built with other kinds of processes, and we believe that'll happen. And custom metal parts. Anybody in here like old cars? You ever wonder what happens if you need an exhaust manifold for a, what's an old car, Doris? 57 Chevy? I don't know.
Yeah. 57 years old.
Okay. If you want a custom part, we can produce those. You don't have to, all you need is a schematic. You don't need anything but a schematic and you can build the part. But basically, we do think, I'm summarizing here, we do think we can take asteroids in and finish metal products out. We can produce these high quality metal parts on demand. And it is a self-recycling technology. So we're really excited about it. Now David Gump's presentation. What we're going to be doing here, there are several different kinds of missions we mentioned in the video. Fireflies are our small one-way prospecting trips. Basically, they fly out to an asteroid to take a look at it. We need to do this because we don't know much about smaller asteroids. If you look at the asteroids that have been photographed, every one of them, the smallest one's 500 meters across, Itokawa, and it's a rubble pile. And all of the bigger ones are rubble piles as well. Every one is a rubble pile. We have never taken a photograph of a monolithic asteroid chunk. That's kind of